In this project, we explore how deep learning can be used to imitate existing path planning techniques. Specifically, we consider 3 neural network-based planning algorithms. We demonstrate the applications of these techniques on the point robot and the non-holonomic car, evaluate them on a variety of maps, and present our results. For the holonomic robot dataset, we generate optimal paths from the A-star planner. For the non-holonomic dataset, we use the RRT planner. We generate 2 types of paths that have the highest cost after running the algorithm for 5 seconds, and paths where the start and goal states are identical except for the orientation. This allows the neural network to generate motions where the robot has to change directions. In general, we use this design for our networks. We pass in the map image through a few convolutional layers, and then pass in the resulting values, along with the start goal states, through the remaining fully connected layers. We also include dropout layers and use them for training and predicting. Dropout layers are useful because their randomness can help us recover from failed predictions. If a network predicts an invalid action, we can pass in the same input to obtain different motions.
So we implemented 2 planners for the holonomic robot. Since for the holonomic robot the action space consisted of 8 possible actions corresponding to 8 possible neighboring points in our grid map, our neural network was a classifier that gave us the probabilities of each action. The unidirectional planner then tried to execute the action with the highest prediction confidence. If that led to the robot running into an obstacle or running off the map, then it tried to execute the action with the second highest confidence. And if all of the top 3 predicted actions failed, then we declared that the neural network was unable to find a path from start to goal. A path was then generated by executing the actions till the robot reached the goal. For the bidirectional planner, it worked the same, except that the path is generated by executing one action from the start position and one from the goal position alternately till the 2 paths meet. In addition, lazy state contraction is performed on the generated path. As an example, we can see lazy state contraction in action here. Here, detours in the path are cut out by looking in the immediate neighborhood of each point in the path to see if some points can be eliminated to shorten the path. And we can see the results of our neural network here. The table on the left shows the success rate of our neural network on a test data set, that is the number of times it was successfully able to find a path from start to goal. We can see that the bidirectional planner works better than the unidirectional planner. We have a success rate of around 52%, and the figure on the right shows a comparison of paths and costs generated by our neural network to the path generated by A-star on the top. On the same test map with the same start and goal positions. As we can see, the cost of the path generated by our neural network is very close to the optimal cost from A-star, especially in the bidirectional planner case.
For the motion planning of a non-holonomic car, we use RRT. Unlike the discrete actions in the previous cases, the action space in this planning problem is continuous. That is, we can control the transitional and the rotational velocity of the robot. The proposed RRT-net is an extension of the unidirectional planner. One peculiar feature of the RRT-net is the presence of the dropout layers, where neurons are deactivated with a certain probability. As shown in the algorithm, we start off with a low dropout ratio to introduce stochasticity. In absence of a viable actions for 150 iterations, the plan is dropped and then the action is predicted with a higher dropout probability. A higher dropout probability here ensures we explore larger action space and avoid getting trapped in local minimas. We generated a testing dataset of 48 maps with random start and goal locations. A plan is termed successful if the position error is less than 10 and then the orientation error is less than 5 degrees. In the cases where the plan was achieved with a low dropout probability, our RRT-net performed very well, as you can see from the plots. The path looks smooth with less abrupt transition. However, mostly in the cases where the solution wasn't found till even 90% dropout, the performance rapidly degrades. The robot performs illogical maneuvers like making sharp turns, taking unnecessary actions, driving entirely backwards and all. For most of the plan, the cost of the path of the RRT-net was much higher since more actions were taken than needed. For the 48 maps, our RRT-net was able to generate the successful plan for 29 cases. Likewise, for 937 test points sampled from the trajectory, our neural network generated the maps for 75% of the time. Also, for the successful plans, the table below shows the mean and the variance of the position error and the orientation error. Although our RRT net was able to find a path from start location to goal location fairly quickly with relatively small position and orientation error. The cost of the path was pretty expensive and unnecessary control signal was being wasted. In this way, throughout this second guided project, we explored the application of deep learning for imitating classical motion planning algorithms. We implemented 2 variants of convolution neural network and tested 3 variants of planners for predicting a feasible path from start location to goal location. We'd like to thank Professor Fox, our TAs Chris and Chung Yun for their guidance and support throughout the quarter.